So yesterday we did our roses, and we said cosine, right? Again, cosine is always a maximum at 0 on this axis. Sine is a maximum at 90 degrees. So, it's always going to lie when it's sine. It's always going to lie along theta equals pi over 2. So we said if we increase n, so this is n equals 1, and it's our circle, right? For cosine a cosine theta, a sine theta, that's our circle. Now, a cosine n theta, when the coefficient of theta is 2 or higher, then, right, we have this. So 2 theta, 4 petals. And again, you see, so one thing I could do is just give you one of these graphs and say, write the equation of these graphs. Okay, so it's a rose, so it's a cosine n theta or a sine n theta. Now, if you're given the blue one, there is a maximum on theta equals 0, that must be a cosine. The green one, there is no maximum on theta equals 0. That must be a sine. Now, what is that maximum radius? How far does it go? 1, 2, 3, 4. So it's 4 cosine theta. 1, 2, 3, 4. 4 sine theta. 4 sine n theta. Now, how many petals? 4 divided by 2. N must be 2. So this is 4 cosine 2 theta. 4 sine 2 theta. You see how we piece that together? And then, you can go from there. Yes?
Is it possible for the maximum distance to be anything?
No. No, because is it possible if you have a graph, if you have a graph on the Cartesian plane, is it possible for them to go to different maxima each time? It's not. It's the same, right? So you always go between maximum, 0, minimum, and it's the same. 4, negative. You know what I mean? Like the amplitude must be the same. Yeah.
So there's an even number of petals, you divide that number by 2 to get n, but if it's an odd number,
then it is n, right? So in this case, where is it? So in this case, again, cosine lies on theta equals 0. That's where the maximum is, but not for sine. Okay, and again, we know it's a rose, so that's a cosine or sine n theta. How many petals? 3. So it's just n. Odd number, it's just n. Okay, and then 4, 5, 6, 7, 8, 9, 10. That's always fun to watch. Okay, all right. Okay, what's up with these ends? Okay, why is it that way? How do the number of petals, how do we figure out the number of petals? Okay, so we're gonna trace this. Now this is 2 theta, so it's gonna have 4 petals, and we're gonna trace this. So take a look. All right, we're gonna go 0, and then maximum radius, back to 0 radius, and then maximum radius, right? So near and far and near and far, right? So we traversed, oh, I don't know what's going on. Oh, here we go. So we traversed this over 2 pi. Yes? Okay. Now let's do, okay, there's a typo here. This should say here 3x, all right? But it is, so this is red, it's 3 theta, and that should say 3x. Okay, now let's see how we're going to traverse this. Okay, so this is 3 theta, right? And so you see that from 0 to 2 pi on the Cartesian, you have 3 full cycles, right? 1, 2, and 3. Do you see that? So you know that that's the graph of 3. All right, so take a look at what's going to happen here. Take a look at how we're going to traverse this. All right, it's slow today. All right, so look.
1 says 2, 1 says 3.
Yeah, we just went over that, remember? Okay. This should say 3. It's a typo. That's what we just said. Okay. Now, take a look at what happened. Where am I here? I just traversed the entire rows, right? But where am I? Halfway. And then the rest, I'm going to traverse the other one. Okay? You see that? That's why you only get half the number, because you end up redoing everything. You see what I mean? Instead of like it's 3 theta, right? Instead of getting 6 petals, you only get 3, because the second half ends up traversing the same curve over again. Do you see that? Do you see it?
And then also when you're like plotting points, you like don't have to do the second half.
Right, exactly. Exactly. So when you're plotting your points, once you complete your rows, 3, that's it. You don't have to go and like repeat the other numbers again. Okay? Alright? So that's what it is. So if this was, let's say, 4 theta, right? Then it would have taken the whole 2 pi to draw 1 rows. But if it was 5 theta, we would draw all 5 petals by, half the curve, and then just traverse the same thing. So that's where the other half goes. It just repeats. It doesn't draw new petals, it repeats the old. Yeah. Okay? So if it's 4 theta, you draw 4 individual petals. But if it's 5 theta, I'm sorry, if it was 4, you draw 8 petals. So you draw 4 and then another 4. But if it's 5, you draw 5 and then the same 5 over again. Do you see it? Okay. Cool. Okay. All right. Let's move on. So this is, again, summary of roses. We know now A is the radius, da-da-da, 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 da-da-da. Okay, lemniscates. Lemniscates, here we have a whole other type. Lemniscates have polar equations of the form r squared equals a squared sine 2 theta, or, r squared equals blah, blah, blah. So, and we see things like this in Cartesian coordinates, right? Where you have like x squared plus y squared equals r squared, for example. So, this would be, let's say, y squared equals r squared minus x squared, right? And then how do we graph something like that? It's a circle, and it's, y equals plus or minus the square root, right? So it's plus or minus the square root when you're going to graph y, right? So you have the same thing, plus and minus versions. So, just keep that in the back of your mind. This is not a circle. This is a lemniscate, so it's completely different from a circle. But I'm just getting you, to like get a feel for what the equation, right, algebraically will look like. Yeah. R is radius, the maximum distance, or the distance from the pole. The distance from the center out. The radial distance out, that's the radius. Okay. All right. Here we go. This is what we have here, right? So I'm not going to graph this on the Cartesian. I think we're over that at this point. But what we're going to do here is we're going to solve for r here. So we're going to get the r values. So to get the r values for this one, let's say, it's going to be the square root of 16 sine 2 times 0, right? Which is 0. Yeah. Okay. Well, a 0. Well, I mean, it's 0. Yeah. Yeah. Let's do one. Okay. So r is, okay, so here we're going to do plus or minus square root of 16 sine 2 times pi over 6. That's like pi over 3, right? It's not like pi over 3. That is pi over 3. So we're going to get plus or minus 3.7. Here, we're going to do 16 sine 2 pi over 3. Okay, how does the value of the sine compared to pi over 3 and 2 pi over 3? How does the value of the sine compare? They're the same, right? So 3.7. Okay. 2 pi over 3? Pi over 3 and 2 pi over 3. Sine is the y value. They're the same. Remember? They're just different sides. Yeah. Okay, so at pi over 2, okay, at pi over 2, this is going to be, the square root of 16 sine 2 pi over 2, which is pi, so 0. No plus or minus there. Okay, here we're going to do plus or minus the square root of sine, whatever, 4 pi over 3. Okay, now 4 pi over 3 is here. What's the sign at that in the third quadrant? What's the sign of the sine? It's negative. So this is going to, oh, there's a sign in there. So this is going to be undefined, right? Because you can't have the square root of a negative number. This is, right? This is 16 sine 4 pi over 3. So that's undefined. And so is this one, undefined. And then this is 0. And here we have plus or minus 3.7. Plus or minus 3.7 because it's the 4 pi over. Okay, but I don't want to rush it. So here, okay, take a look at what happens there. This is now the square root 16 sine 2 times 7 pi over 6, which is 7 pi over 3, which is 2 and a third pi, so we're back on the positive. So it's positive, so it's plus or minus 3.7. So you get the same value as these because you're exactly at the same point as those. Okay? And then here you get the same point as that one. And then this is 0, undefined, undefined, 0. What we're missing here are the pi over 4s, and something special happens at the pi over 4, so I'm going to put that in right now. Yes?
So when we have undefined points, we just skip going completely.
You skip whatting them?
Just go from pi over 2 to 5.
Yeah, they're undefined. There is no point. Okay? So the pi over 4, right, which is here, right? At pi over 4, no, I don't have, at theta equals pi over 4, what do we get? 16 sine, 2 times pi over 4, which is pi over 2, which is 1, so that's 4, and that's where the maximum happens, right? That's the maximum. Because, okay, so remember this is a sine. The maximum happens at pi over 2. This is 2 theta, so the entire 2 theta must be pi over 2. That means theta must be pi over 4. Pi over 4 times 2 gives you pi over 2, so that's where the maximum happens, right? And then here there is a 5 pi over 4, and r is also 4. Okay, let's do this, guys. Oh my God, I love this stuff. Okay. Poles, right? Okay, so at pi over 6, we got 1, 2, at 0, we got 0. At pi over 6, we got 1, 2, 3.7. At pi over 4, we got 4. I'm sorry. Wait. Let's do that again. We do the negatives too. So also negative here. And then at pi over 4, we get negative 4 as well. Okay. Pi over 3, we get plus or minus 3.7 again. Okay. And then 0. So far, what did we trace? We basically were tracing something like this. How cool is that? And then, okay, so here, I completed a lemniscate. And then, okay, so 2 pi over 3, undefined, 5 pi over 6, undefined. At pi, we're at 0. I drew that, you just didn't see me. I'm drawing it now, 0. Okay, 0. 7 pi over 6, all right, I get plus or minus 3.7. The same thing's back. 5 pi, well, my pi over 4 should have been there. 5 pi over 4, I get plus or minus 4, and then plus or minus 3.7, and then 0 again. And then it's here, undefined, undefined, back to 0.
So just repeat.
Just repeat. Okay? So this gives you a lemniscate, a whole lemniscate, 2 poles. This gives you, this repeats the lemniscate. Got it? Wow. So you draw 2 in 1 cycle. And I like these because they look like the p orbitals in chemistry.
Yeah, they so do. Yeah.
They look like the p orbitals, right? And then the s orbital would be like in the center here.
I love that. Drawing those are so cool.
Right? And then maybe we could come up with a polar equation for the d orbitals too.
Let's do it.
Those are like the roses.
So the word cosine would be like almost sine.
Yes, it would.
And then also, would it ever have more than 2?
No.
So no matter
No, because no matter what, right, sine and cosine alternate in the Cartesian plane, being positive and negative, right? The negative ones, because you're taking a square, are always going to give you undefined. So so it's going to be, whether it's sine or cosine, okay, so there's a good question here. Can you have more than 2 of these, right? Well, the thing is, sine and cosine, right, are on the unit circle. Half the time they're positive and half the time they're negative, right? They're positive in 2 quadrants, negative in 2 quadrants. That means, and under the square root, they're going to be undefined half the time and defined only the other half. So there is no other way it could look. And then Claudia, hit another point where if this was the cosine, it would be along that horizontal axis. Okay? And
it'd be like that.
Yeah. If it was negative, right? If it was r squared equals, if it was negative r squared. So now, let me tell you something else though. This distance, that's not a, that's the square root of a, right? I mean, that's this number, the square root of that number. Okay? So that's right. So that's root 16. It is a, you're right. You just have to take the square root of that number. Okay? Yeah. Just to make sure, this pi over 4, 5 pi over 4, it goes here. Right? Okay. Next, last but not least, spirals. Spirals of Archimedes. Okay, so there was like a little thing in math where there's like a controversy, and there was a spiral of Archimedes, and then there was a spiral of Bernoulli, and they're different spirals, and there's a little bit of friction between these two. They're like competing for the top spiral, and nobody ever wins. Okay, but we're gonna do spirals of Archimedes right now. These have polar equations of the form a theta plus b. There is no what? There is no sine or cosine. It's just a theta plus b. So let's just think about this. Theta starts at 0 and increases, right? So when we're looking at the sine of theta, okay, sine of theta, as theta increases, sine of theta starts at 0, goes up and down and up and down and up and down. Sine of theta as a function oscillates as theta increases. But if your function is just y equals theta, theta increases, y increases. So if r is just a theta, when theta is 0, r is 0. When theta is 1, r is 1. When theta is 2, r is 2. When theta is pi over 6, it's even bigger, and then 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 bigger, and bigger, and bigger, and bigger, and bigger, and bigger. So radius just gets bigger and bigger and bigger, okay? So yeah, so as theta increases, r increases proportionally, right? So which means spirals will radially extend outward with no bound. Okay, so we're gonna do not all of these, but a couple of these, just to give us an idea. So we're gonna graph r equals 3 theta, and here we get 0. I'm just, 3 times pi divided by 6, that's 1.6, and 3.1, and 4.7. And here we have 3 times 2 pi over 3, which is 2 pi, which is 6.28. And then 7.9 and 9.4. And I'm just going to stop there. Okay. Okay. So I will also relabel this to 2468. So now, when theta is 0, we're at 0. At pi over 6, 1.6. Then 3.1. Then 4.7. Then 6.3246.3, and then 7.4 is somewhere, where's 7.4? At 5 pi over 6. And then at pi it's 9 point something, so it's like out there. So look at what it looks like. You see how it's a spiral, and it just keeps like spiraling outward and outward and outward. Okay? Right. Now, if you had, let's say, r equals theta plus, 2, okay? Then you start at 2, and then, you spiral from there. Do you see what I mean? Okay? So that's how, it's just a translation, okay? All right. Symmetry. Okay, so just like in Cartesian coordinates, it's possible to use a function's symmetry to reduce the number of points needed to sketch something. And there is a reason why I did these at, such great detail, because I wanted you to see how things are traced and then how sometimes they're retraced, because you're going to use that. There is no other way to get that deep understanding, okay? Now, but once you have that understanding, you can now, use this stuff to your advantage. So graphs of polar equations can be symmetric with respect to the line theta equals pi over 2, that vertical line, the polar axis, horizontal, or the pole. Okay, so just like in the Cartesian system, something is symmetric with respect to x-axis, y-axis, or the origin. Same here, polar axis, pi over 2, or the pole. So this one, for example, right? What is it symmetric with respect to? The pole, right? And, this one? Right, okay? Okay, so you could see here, for example, that this one, the one on the very right, that's blurred, is symmetric to what? The polar axis, right? The polar axis, because if you fold it vertically, okay. So here's how do we test well, here are some more pictures, right? Symmetric with respect to pi over 2, theta equals pi over 2, right? The polar axis, and then the pole. In the Cartesian system, we test for symmetry, right? If we're going to test for symmetry with respect to the x-axis, what do? We switch y to negative y and see if we can get the same function back. X to negative x right. So we're used to replacing x with negative x, y with negative y, and then both. Well, here we do the same thing. If you want to test with respect to the polar axis, you switch theta with negative theta. Why? Because if something is symmetric with respect to the polar axis, right? Whether you have theta equals pi over 6 or negative pi over 6, your r value is the same. Do you see that? So, you replace something and then you see if they're the same. All right, with respect to theta equals pi over 2, you replace r and theta to negative r and negative theta. Okay, because if you were to switch to negative theta, right, where would that give you? Where would that take you? Negative theta would take you here, but then negative r takes you back there. Okay? So negative theta brings you there, and then negative r will take you back there. And then if it's symmetric with respect to the, I know it's a little bit counterintuitive, but if it's symmetric with respect to the pole, right, then take a look here. If this is a radius of 3, then the opposite would be a radius of negative 3. So you have to replace r with negative r. Okay, so that's where they come from. All right, so if something is, once you determine that something is, let's say, symmetric with respect to theta equals pi over 2, right? All you would have to do is graph from negative pi over 2 to pi over 2, and then copy the rest. Okay, as it says down there. Most of the time, okay, you know me, never memorize. Most of the time, based on what I've given you, okay, cosine is going to be symmetric here, most of the time you will know what to pick. There is no rule, okay? You will know what points to pick and then to mimic, because I've now told you that if it's a cosine theta, it's here. If it's a sine theta, is here. Negative a sine theta is here. So you will know. But don't memorize this stuff, please. Like, don't memorize this. Okay? Don't memorize that. Yeah.
So when we first get an equation before we start graphing, you suggest that we test it for symmetry first before we
I do. We're going to do one right now, actually. We're going to do a whole bunch like that. Okay. These are everything that I've shown you before, all in one page. I just cut and paste before. So notice the spirals and the lemniscates. Okay. Let's talk about maximum R values. We already know. It's not a secret. The maximum R value is the farthest the graph goes, okay? We've been doing it since like 2 days ago, all right? So that's the furthest point the graph reaches from the pole. Okay, how do we find this algebraically? You're going to find first the theta values for which R is maximized. Okay? What does that mean? If you're dealing with sine, right? If you're dealing with sine, where is sine a maximum? At 0 or pi over 2's? At the pi over 2's, right? So then you plug in, okay, if theta was pi over 2, what would the value be? 4, 6, 16. Okay, that's the maximum R value. So you're going to be looking for the location and the value. Okay, I just realized I have to like fix my wording here. If R is 0, obviously, for a certain value of theta, it means the graph intersects the pole, right? We know this because if y equals 0, it intersects the y-axis and so on. All right. So to find maximum R values and their locations, okay, you know the wording I had to fix up there? I just did it here, right, in this box. So here's what we do. First, determine the values of theta for which the parent of the particular function attains maximum values. Like I just said, is it sine at the pi over 2's? Is it cosine at 0 and pi and 2 pi? So for example, sine of 0 is plus or minus 1 at the pi over 2's. Okay? Now, to find the maximum R value, evaluate the specific function at the value of theta. All right? To find the location of the maximum R value, set the angle equal to the maximum angle and find theta. So for example, you know you have sine. Sine is a maximum at pi over 2. Now, if it's sine 3 theta, then you say 3 theta is pi over 2, 3 pi over 2, and you solve for theta, just like we did in section 4. Was it 5.3? Okay? Right? I know. Okay. So, more like September, but it's okay. So, the zeros of a polar function are the values of theta where the radius from the pole is 0. Okay? Again, like I just said, these are the same points where the function would cross the what in the Cartesian coordinate plane? When it's 0, the x-axis, right? Okay. To find zeros of a function, you guys all know this. To find zeros of a function, set the function equal to 0 and solve for theta. Chapter 5, right? Find the zeros of this. Well, you want R to be 0. So you want this whole thing to be 0. So we say 0 equals 1 minus 2 cosine theta. Then we reorganize. And 1/2 is equal to what in this equation? Cosine theta. So what's theta equal to? Pi over 3 and 5 pi over 3? Pi over 3 and 2 pi over 3. Oh, for cosine, I'm sorry. Sorry. Okay, sorry. All right, let's do one. Ooh, we might make it. Yes, we're gonna do this. Why haven't I? Okay. All right. Identify the type of curve given by this. By 2 cosine 3 theta, right? So this is a cosine and theta. What kind of curve is it? It's a rose. Yes. It's a rose with 3 petals. Determine the symmetry. So let's talk about symmetry. All right? So let's see polar axis. Right? For the polar axis, what do we plug in? Theta equals what? Negative theta. So let's see. R equals 2 cosine 3 times negative theta. Do we get the same function back? We do, because cosine is an even function and it engulfs that negative. So you're done. It's symmetric around the polar axis. Yeah. Cosine of negative theta is the same as cosine of positive theta. Because if I have cosine of negative 11 pi over 6, or pi over 6, right? It's still, the x value is still the same. All right, let's do zeros. Let's do zeros. For the zeros, I'm going to set the function to 0. So 0, okay, so 0 is equal to cosine 3 theta. All right, now, where is cosine equal to 0? Where is the cosine function as the default equal to 0? Pi over 2, 3 pi over 2, 5 pi over 2, and so on. Now, if this is 3 theta, how many total cycles are in this? 3. So hang on. It's 3 total cycles, right? Each cycle hits 0 twice, so we're going to have 6 of these, right? So we're going to do 3 theta equals pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, 9, and 11 pi over 2. Okay, so how do you know when to stop? You can either, rationalize it the way I did, or keep solving these. So theta is now pi over 6, 3 pi over 6, which is pi over 2, 5 pi over 6, 7 pi over 6, and you have to go until you complete all of them, or like until 2 pi, right? So 7 pi over 6, I'm still here, and then I need to go until I've exhausted all options until 2 pi. So 9 pi over 6, that's 3 pi over 2, and 11 pi over 6. So those are all the zeros. Three theta, 3 petals, right? And so we said, it's going to go 0, maximum 0, maximum 0, maximum 0, and then it's going to traverse again. Okay. Next, we do maximum R values. So for the maximum R values, you have to find the location and their actual values. Okay, so R values. All right, so, or let's do maximum. So first, we're going to do the location. Okay, cosine of theta is max at theta equals what? 0, 0, 2 pi. So, okay, so we're talking about, when I say max, here we go. Let me specify plus or minus 1, right? So that's going to be at 0, pi, and 2 pi. All right? So at theta equals 0, pi, 2 pi, which means because our angle here is 3 theta, we go 3 theta equals 0, pi, 2 pi. So those are the locations. And number 2, we want to actually find the maximum R value, like the actual value. Okay. So at theta equals 0, cosine is positive 1, right? So here's how I do this. Theta equals 0, I get positive 1, which means in my value, this is 2 cosine 3 theta, it's going to be the positive maximum, positive 2. Right? At pi, you get negative 1, so that's going to be negative 2. Right? And then at 2 pi, it's going to be positive again. So
you don't use the one, you don't use the pi and 2 pi?
you could, you would just have to like plug that back in. So it'll, look, if you plug in pi over 3 into here, what do you get? Pi.
Oh,
So you could either, you could do either or. You see what I mean? So then the maximum R values happen at 2, 0 degrees, negative 2 pi over 3, not degrees, we're going to go in radian, and then 2 and 2 pi over 3. Yeah. Okay, so let's graph the sky. So when you do this, okay, I haven't asked you for points, right? I'm okay with if you just use this. So you say, all right, so 2, right? We get a maximum there. At pi over 3, it's negative 2. 2 pi over 3, it's positive 2. And then it's 0 everywhere else in between. So I'm fine with you drawing your rows like this. Okay, just, we'll try to make it even. What did I do? Okay? Yeah. So we test for symmetry around the polar axis. For that we do r squared is equal to 8 sine negative 2 theta, and you don't get sine back for that one, so that doesn't work. For theta equals pi over 2, I switch both r and theta. Again, you might get r back, but not theta, so that doesn't work. Theta equals, the pole, we're gonna just switch r, and that's gonna work. Right? So it's symmetric around the pole. And we knew that. But now we proved it. We showed it. Okay. Zeros. We're going to say the function is equal to 0. Okay. So where is sine equal to 0? At 0 and pi and all that good stuff. Yeah. What is?
Like, so r is plus or minus the square root of 8
r is 0. Are you talking about the zeros? No, for the zeros, you set the function to 0, so whether it's squared or square rooted, it wouldn't matter. Okay, suppose you did r as the square root. Right. So 2 theta, so sine is 0 when the angle is equal to 0, pi, 2 pi, 3 pi. Well, you gotta go until you can solve through 2 pi. So let's go one more. So theta is 0, pi over 2, pi, 3 pi over 2, 2 pi. Okay. Right. So let's do radius. Sine of theta equals plus or minus 1 at theta equals what and what? Right, the pi over 2's. So here, r angle 2 theta is going to equal pi over 2. 3 pi over 2. Again, we got to go until, we get all of them up to something. Huh? 2 theta, because our function is 2. Okay, so here it is. Sine is a maximum when the angle is pi over 2 or 3 pi over 2. The angle here is 2 theta. That's the angle. So we say when the angle is equal to blah, 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 right? When the angle is equal to blah, 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 and then we solve for theta, the variable. So there is something important that happens here, though. And then 2 theta is 7 pi over 2. But do we want minus 1 in this case? Because you're going to take a square root. It's undefined at the negatives, right? Where is it negative? Here and here. It's undefined, so we take those out. Right? Because it's a lemniscate. It's undefined half the time. So then theta is pi over 4, 5 pi over 4. Okay, what is that maximum value going to be? It's going to be the square root of 8. So that's going to be 2 root 2, right? So max R value will be plus or minus root 8. Because that wasn't R squared up there. This is R squared. So now it's going to be, well, not plus or minus root 8. Just, well, yeah, no, plus or minus root 8. Okay? So it's going to be plus or minus root 8 at pi over 4. Plus or minus root 8, 5 pi over 4. And root 8 these days is 2 point something, right? So at pi over 4, it'll be 1, 2 point something. And then at 5 pi over 4, it'll be 1, 2 point something. Don't go wasting time plugging in root 8 or root 6 or root whatever in your calculator. You're not going to get it to NASA precision on this axis anyway, right? On that grid. So don't waste time. There are other things where you can spend your time. And there we have it. That's our cute little lemniscate. Okay? So I don't start you off like this. The book does. I don't. Because then you have no idea what you're doing. It's super worthwhile. First time around, to go through them ad nauseum like this, right? Like we did. Okay? It is useful. Because think about how you graph parabolas. By the time you get to using the shortcuts, you've done so many over the years. So we can't just, give this to you in 2 minutes and go here. Okay, one more. Okay, all of you musical people. During a concert, a directional microphone was placed facing the audience from the center of the stage to capture the crowd noise, right? You know what we're talking about? Okay. Basically, oops, what happened? Okay. The area of sound the microphone captures is represented by that. Okay? What is that? So, that's a cardioid. Okay, because it's A plus B cosine theta. Okay? And A equals B. So it's a limicin, but a cardioid. Okay? Right? Suppose the front of stage faces due north. So like here, like this is the front of stage. Graph the polar pattern of the microphone. So our cardioid, right? The maximum distance is going to be a what? Here. 2A. Right? So that's going to be a 7. Okay? And now this is a sine. So is it maximum on the polar axis or at theta equals pi over 2? At theta equals pi over 2. So go ahead and draw that cardioid. Okay? So we're going to go by 2's, and it's going to be 2, 4, 6, 8 here. So 7 here, right? So there is going to be a little dimple. And it's going to go out like this. Okay. I am eyeballing a little bit. Okay. Next. Well, for this particular problem. Now look, if I ask you to, draw precisely, with the chart and the points, I want you to do that. But for the purposes of this and the fact that I have 3.5 minutes, this is what we're going to do. But this is what it looks like, right? Because what is it? It hits a maximum here, and then, the radius, okay, it's sine. how does sine work? Sine starts at 0 and increases. Okay, so starts at 0 and radius increases and so on and so forth. So that's how it looks like. So there is a little dimple there. Okay, so this is the area of the microphone. So this is the area. If the microphone is here facing the audience, that's the area from which it's conducting sound, or it's attracting sound. So like if you're sitting outside of that cardioid, no matter what you say, the microphone isn't gonna take your noise. Okay? Huh? Most, yeah. There is yeah. It depends on the microphone, all right? So, so again, that's what the point of this problem is to define, right, in English, what it is that this is showing you, all right? So the microphone, what does it tell you about the microphone, about the pattern? So it'll pick up sound. It'll pick up sound. What are the units here? Does it say? No, it's distance. The radius is distance. It doesn't say. So we'll work with units. 7 units away. You know, at or in front, right? Like directly in front of the microphone, right? Well, 0 degrees. Like if the microphone is facing out, okay, the microphone is facing the audience, right? So if somebody is sitting directly opposite from the microphone, then 7 units away. And okay. And then what's the minimum? Up to, well, not 0, up to, like, to the right or left, it's gonna go. Okay, so what I'm trying to say is, if this is 0, what, up to 3.5 on the sides, right? Okay, all right, so this will be due next time, and next time is tomorrow, okay? Yeah.